Hello students, I am Chakraborty from Department of Geology, University of Delhi. Today our topic of discussion is secondary migration of hydrocarbon. Once you go through this module, you will be able to know that what is the meaning of the migration of hydrocarbon and what is the secondary migration. What are the mechanisms by which the hydrocarbon undergo the secondary migration? How much distance hydrocarbon can go for the secondary migration? Also, you will be able to understand that which are the basins which should be prospective and we should go for the hydrocarbon exploration and which are not. So, all these issues that will be discussed in this module, which I will discuss with you in the name of secondary migration. Now, we have already discussed the primary migration, that means how oil that migrates through the source bed or it moves from the source bed to the reservoir bed or the carrier bed. We have also discussed with you in the name of primary migration that how within the very fine pore spaces of the fine grain rocks the oil try to move, and that initiates the primary migration of the oil. Now, my today's discussion is something different. That is, once the oil comes out of the source bed or it comes out from the source bed to the carrier bed, then how it moves through the carrier bed to the reservoir. Because we all know that where oil forms, we do not get oil there. So, if we do not get oil where it forms, then there must be some migration, and that migration process, which is very important within the carrier bed, that we call the secondary migration. So, what is the fundamental difference between a primary migration and a secondary migration? The primary migration, it happens in a very small pore spaces. It happens with when the oil globules, they are very small, they are microscopic or submicroscopic, and then that migration we call the primary migration. And what is secondary migration? When the oil globules, they are much larger comparatively in size and they are migrating through coarse grain rock. That coarse grain rock where the pore spaces are relatively larger and they are more interconnected with one another, then the mechanism of that we call it the secondary migration. So, when we talk about the secondary migration, we essentially talk about the coarse grain rock, suppose the sandstone. And as we know that the sandstone again can be of different type, from fine grain sandstone to coarse grain sandstone, from good sorting to poor sorting. So, there can be different kind of permeability within the sandstone, and that permeability basically plays a major role that how the hydrocarbon that will pass on through the network of the pores within the coarse grain sandstone. Now, all this knowledge that how hydrocarbon passes through it, once it come out, that comes under the domain of the secondary migration. Now, I come on to first discuss a little bit about the primary migration before I go in detail into the secondary migration. Then when there is a primary migration, what we see that there is the microscopic or submicroscopic hydrocarbon, and they are present abundantly within the pore water. And as they are abundantly present but in a very tiny size, they normally is guided mostly by the hydrodynamic condition of the source bed or the initial reservoir bed, but do not control mainly by the buoyancy, because the size is too low that the buoyancy factor will start operating into that. This basically lead to the secondary migration component, that when the oil globules they increase in size, then how buoyancy plays a major role in the secondary migration. So, when people started appreciating the secondary migration, then people started thinking that what may be the reason behind the secondary migration, and number of different factors that people talked about, that this is why there is secondary migration, which include the initial deposition of the sediment at what rate, that the pressure of the oil, the size of the globule, the temperature. So, there are many factors that people talked about to tell about how the secondary migration of hydrocarbon takes place. But three factors which finally people came into a consensus view that which plays the major factor, those three factors are: number one, it is the buoyancy; number two, capillary pressure, and number 3 is hydrodynamic condition. So these are the 3 factors which people think that they are some of the most important factors in the secondary migration of hydrocarbon. Now, how these 3 factors they play the role, that is the core of the discussion of secondary migration and how they really control the entire secondary migration process. Now, once we go to the secondary migration, we must first appreciate that the secondary migration essentially happens into 2 major conditions. One is a hydrostatic condition, another is a hydrodynamic condition. Now, what is hydrostatic condition? When the pore water, they are in a static state, that they are not moving, pore water is not moving, there is no water flowage. So the pore water is a stationary condition, we call is the hydrostatic condition, and there the major force which will be operating for the secondary migration, that is the buoyancy force. And then come the hydrodynamic condition. We will discuss both the conditions. Hydrodynamic condition, when there is a physical flow of the water, and that basically controls that, how it controls the secondary migration we will also discuss. First, coming on to the hydrostatic condition, as we discussed that the buoyancy is the major force in the hydrostatic condition, and it is counteracted by the capillary pressure. So first is the buoyancy force. What will be the buoyancy force that will be operative there on the any petroleum component in contact with the pore water. So the buoyancy force that will be Z0G Now this Z is the column of the hydrocarbon that it will raise because of buoyancy. So Z, this is the height, G is acceleration due to gravity, rho W is the density of water. So you can see that the entire force, buoyancy force, it is actually the density difference between water and the hydrocarbon component. So the entire function is the density difference between the 2 phases. So rho W, that is the density of water, pore water, that depends upon temperature, salinity and the thermal expansion of water. You come on to the density of petroleum component, it depends upon the composition, the temperature and the coefficient of thermal expansion. Now this force, that is the buoyancy force, which basically operative by which the oil try to rise through the pore water, it will be counteracted by the capillary force. Now what will be the capillary force? The capillary force will be this, where this one, this is the interfacial tension. So this is interfacial tension and RT and RP, this is nothing but the radius of the oil globule and the reservoir pore space. So this RT and RP, they will be, I will be further by figure, I will be discussing you what is really mean by RT and RP, but these two are the radius of oil globule and reservoir pore radius. Now when it is a equilibrium condition, in a hydrostatic case we are discussing in a equilibrium condition. Now in a equilibrium condition, the buoyancy force that will be equilibrating with the capillary force. So if we see that how the buoyancy force that is equilibrating, so we get that Z0 G rho W, this will be equal to So this will be balancing when you come to the equilibrium, and if this equilibrates, then what will be the maximum height a oil globule or a oil petroleum component that will rise within the hydrostatic pore water condition? The buoyancy effect will make the maximum rise, that is this one, that is the amount of height. This is nothing but this is divided by, so this is the maximum height the oil that can rise through water, with the water which has a density rho 0, rho w, and the hydrocarbon component on oil that has a density of rho o. And this height, what we call that the critical height. This is what we call as the critical height. Now, if the condition is that this factor, that is Z0 G, this is more than Rp. If this condition is that means it is a non-equilibrium condition. In equilibrium condition, what I have described, that these two will balance each other. When the equilibrium is disturbed, that means they are not in balance with each other, then this factor that is more than that. Now, if this factor is more than that, at that time the height of oil that will be more, and you will get that the active migration because of buoyancy of the oil that is happening. But if this factor, that is 2 gamma, this factor becomes more than this, then we get that the active buoyancy related oil migration will be prevented because the capillary pressure is more than the buoyancy pressure. So I discussed the three cases. In one case, when you have the equilibrium between the two and you get the critical height of the oil droplet, what it will be there because of the buoyancy effect. One case where your buoyancy force is more than the critical, and then when the capillary force that is more than the buoyancy force. So all the three cases I can have, and that basically define that how buoyancy that will be active on the oil. Now once we discuss this, then the second question comes that through the very fine pore throats, how the large oil globules they will move. And that really is a very important concern, because you know that in sediment, if I have sediment and the pore throats are very narrow, and I have, suppose I have a oil globule, this is oil, and it has to pass through this pore space. How it will pass through this pore space? Even if it has a buoyancy effect, it has to pass through this pore space, and then as it has to pass through the very narrow pore space, it will, what are the factors that will be very effective? So as you know that if we take the sediments, are settled sediments, they are like this, and a oil globule that is of this size which has to pass through this narrow pore space, that become a challenge, that how really it goes through this narrow space. So it is interpreted by that what really controls its movement through this narrow pore space, that is actually the internal pressure of it, internal pressure. And how we define the internal pressure? It is defined as the interfacial tension, and this is basically the radius of the globule. So this becomes the radius of the globule, and this is the internal pressure. So because of this internal pressure, actually and the buoyancy effect, the oil globule first start and try to enter through the pore space, and if you see its geometry, then the geometry of the oil globule, it will be like this. This portion here, if we see, this is basically the Rp and this is Rt. There are two different kinds of the radius that is developed. Then what we get, that 2 gamma by Rt, this will be more than by, this will be Rt. This will be more than this, because the Rt is larger than Rp, and this higher internal pressure that will try to drive this globule more towards up against the pore water that is there. So this interfacial tension actually takes care of that pore water and the oil globule, what is the interfacial tension between the two. And this, once this internal pressure forces it to it, then it takes a shape something like this, that is the dumbbell shape, it takes a dumbbell shape. And in the dumbbell shape, when it comes, that this R and this R, that becomes same. So instead of this, at this stage, that if this is A, that at the stage B, that in both here and here, the pressure that becomes same here and here. And that at that condition, again the buoyancy effect that comes into operation, and that buoyancy condition, finally what happens, that the oil globule starting from here taking a shape like that, and then the internal pressure coming into operation, it is forcing it up, taking a dumbbell shape, and finally it crosses the pore throat boundary. So the two effects that is very important, one is the buoyancy force, and the second is the internal pressure that basically allow the larger oil globule to pass through the narrow pore throat. So once we discuss this, all this, that what are the processes that is operative in the hydrostatic condition. And in case of hydrostatic condition, if these two processes operative, that is buoyancy and the capillary, we know that the entire oil that will move as per the thickness of the bed. Unless you have a fracture or you have some kind of the joint which is permeable in the overlying cap rock, normally the height of the oil column that will be same as that of the thickness of the bed. But often what we see, and what we expect in that condition, because the stationary pore water, we expect that the oil water contact, the oil gas contact, all these should be horizontal in nature, because the water is stationary. But if there is a movement of water, when we have the hydrodynamic condition, we will now discuss that hydrodynamic condition, that how it happens. In the hydrodynamic condition, as there is a water flow, that the oil water contact, the gas oil contact, or the gas water contact, we will see this, all these contacts there from the horizontal, they will be deviated into more inclined, and so much so that sometime that the oil and gas, they will be separated from one another in the downslope side. So if we go to that kind of discussion, that what will happen, by that I can draw a diagram and discuss that how really, what really we mean by the hydrodynamic condition. So this diagram illustrates the hydrodynamic condition very well. First case, that is the case 1, what is drawn on board, that shows there is no movement of water. And you can see this is an anticlinal reservoir, and in this anticlinal reservoir we have a contact between water, then oil, and the topmost is gas, because this is the lowest density, the gas that is in the topmost part of the structural trap. And what we see, that there is a contact between water and oil, and there is no contact of the gas and water, because the only contact available with gas is that of oil, not of water. And both the contact that are nearly horizontal. Now there you start increasing the strength of water flow in the system. If the strength of water flow increases, so what we see, that the first the oil water contact that started getting inclined, but the oil gas contact still remain horizontal. Why the oil water contact? Because that is of the maximum energy, the oil water contact that has the maximum energy, so it will be disturbed fast by the water flow and it will start becoming inclined. Once the water flow further increasing, because this is the direction of the increasing strength of the water flow, then you see that the oil that will be separated, start separating from the gas still remain here, and the oil it become inclined, and you first time start developing the gas water contact, which normally you do not get, you always get the oil water gas contact, but this is the first time we start getting the gas water contact. And at the same time, if I further go on increasing it, I just slightly change it, it also becomes slightly inclined. Then what we will see that the further increase in the water flow, then you get the gas water contact that will be little inclined, but there will be a full scale development of the gas water contact, and also the oil it is separated from here, and there is a separated accumulation of the oil in the further downslope within the limb with the development of the new oil water contact. So this separation of the hydrocarbon phase from this original site to the separate site, this basically is the reason for the hydrodynamic system, where there is a active water flow in the system. It causes the water oil contact, the gas oil contact, instead of horizontal it becomes the more inclined. Now I will go into this with more detail that why really it happens. So to describe that how really the hydrodynamic system that operates, we must have an idea about the isopotential surface. What is the isopotential surface? The surface along which the potential is always same. That is what we call the isopotential surface. Now I will construct that how is the isopotential surface of water, oil and gas, these three systems that operate in an anticlinal system. If you see, suppose there is an anticlinal system and there is a water flow. So if there is a water flow, the isopotential surface, they will be something like these, that the isopotential surface, if you start at 28, 26, 24, 22, like that you can go to 0, and because of the difference in the potential between the two surfaces, the one is 28, other is 0, so there will be a flow across the potential from the high to the low. That is how it operates. Now coming on to for the gas what we get, that the so in case of gas, that the isopotential surfaces, they will be like this, because gas has a high buoyancy force and it will be moving up. So the isopotential surface will be very low gradient, and then what will this is be minus 14, minus 12, minus 10, minus 8. So these are the isopotential surfaces that will be telling you that what direction the gas will move. Coming on to the oil, the isopotential surfaces, they will be like this. So it will be suppose 7, then 6, then 5, 4, 2, like this, the isopotential surfaces of this. So you can see there are three phases which are cooperative. They are occurring at the same time and operative at the same time, but three have the three different kinds of isopotential surface. Now coming on to that, how really in an inclined reservoir the character of a oil globule where the water is moving. Suppose I have a inclined bed, the oil globule, because of the movement of water, that will be changing in the form of a stringer. This is suppose the oil and there is a water movement. So the oil will become a stringer, and then what will be, so what is the height of the water oil column? This becomes the height of the oil column, that is what is Z. And what really guide the movement of this oil, suppose this is x1 and x2, what is the potential difference between the two, that basically controls the movement of that oil globule, and the height of the oil globule, that will be this point and this point, what is the vertical height, that is the height of the oil globule or the oil stringer. Now if the water that moves up deep, then what will happen, that the stringer length will be small. If the water is moving down deep, so because the action of gravity is also helping, the stringer will be more elongated. And the height will also be depending on that what is the relative density, what component of the hydrocarbon that is basically operative and what is its relative density. Now coming on to this situation, that all the three if we get together, then we see this is a kind of condition that we develop, that this is the buoyancy force, that is PB, that is operative. This is the hydrodynamic force, that is the pH, that is operative, and this is the Py, that is the confining pressure. That is the anticlinal system. There are the three different forces that is operative. We will have a gas isopotential surface like this. We will have a oil isopotential surface like this, and we will have the water isopotential surface like this. So this is one above another. So that is the combined system that you will get when the three phases they are cooperative and they are coming under the influence of this, the buoyancy force, which is the maximum for gas, and the hydrodynamic force, that is for the water, and then how oil that will be basically operative. Now because the isopotential surface of oil that is very steep, what will happen, that if the stiffness of the limb of the structure, that is the anticlinal structure, if it is more than the stiffness of the isopotential surface of oil, then only the oil will be trapped in the structure. But if the deep of the structure that is lower than the deep of the hydrocarbon isopotential surface, then the oil will escape from that. And the diagram what I initially had drawn, that you have a gas and the oil that is shifted here, oil is shifted here. So what is happening, that the isopotential surface of the oil is like this, and when it is have a water flow, then the oil, the isopotential surface will try to become the more high gradient with respect to the structure. And whenever this isopotential surface has a higher gradient than the limb gradient, then it will definitely escape. But as here we had a further high gradient of the limb, and that is more than the isopotential surface, so that oil got trapped in there, where again the deep of the limb got increased with respect to the isopotential surface. But if it doesn't increase, if it continues like the low gradient, then that oil will escape from the structure, and I will not have the oil in that structure. So that is a very, very important thing in a hydrodynamic system. When the meteoric water flow operated in a hydrodynamic system, what is the inclination of the strata? And if the inclination of the strata that is more homoclinal and it is very low gradient, so there is a very high chance that in a hydrodynamic system that the oil, and if the water flow goes for a long time, even the gas that will escape that structure, and it will, despite it initially was a trap and it trapped the hydrocarbon, we will not get any hydrocarbon once the large scale operation of the meteoric water flow that will be there within the system. So that basically talks about that how the hydrodynamic system, that is very important for making the hydrocarbon trap, its location within the trap, whether we will expect the occurrence of hydrocarbon in the trap or we do not expect that in the trap. Now based on this, that the hydrocarbon basins, they have been classified into three types, that we get some basins that are called the juvenile basins, where the water flow, they are mostly in the form of the centrifugal force and through the lateral movement along the side. So it normally is not juvenile here, doesn't mean the new. It is basically that these basins do not have a major effect of the meteoric water flow, because the water flows in these basins, they are mostly in a centripetal form and through the lateral flank of the basin, not in the central part of the basin. Some of the example is the North Sea, where the Gulf of Mexico, you get then the northwestern Sahara. So all these are the basins which are the good basins for hydrocarbon, where the meteoric water action is very limited. Now we get some basins, those we call the intermediate basin, where you have a centrifugal force of operation, and some water they are moving to the central part of the basin, and depending upon the relative erosion of the different strata, some of the strata can come under the influence of the active movement of the meteoric water, and these basins may or may not have. It is not that there is no guarantee that every time you will get hydrocarbon there, but we do exploration, and they may or may not have the potential of the hydrocarbon occurrence in those basins. Suppose the Persian basin, the central Tunisia basin, all these basins, they are in this category. And then we get another type of basin, what we call the senile basin, where there is a large, it is a long time the movement of the meteoric water within the basin, which made the basin non-prospective, and we do not get any hydrocarbon within that basin. So when we discuss that how much a hydrocarbon that can migrate, we have seen that in the hydrostatic condition it is the buoyancy force, and as far as the thickness of the carrier bed or thickness of the reservoir bed, the hydrocarbon can it can move up. But then the permeable bed that acts as a cap rock that do not allow it to further move. But if you have a fracture, you have a joint plane, then the oil column can further move up. But in a hydrodynamic condition, that we have seen that depending on the amount of water flow, depending on the bed inclination and the isopotential surface of oil, the oil can be separated even from the gas contact, and there may be a separate oil pool, or both oil and gas, they can be totally detached and they can go away from the system as well for the large scale movement for a long period of time. So all these, so when we try to reconstruct the history of this hydrodynamic process, what might have caused this large scale movement, then the people use some use of the tracer, the non-alkylated, the benzocarbolate, that which is a tracer commonly used, which do not depend upon the degree of oil or the type of oil and the maturity of oil, and that tracer helps us to identify that how much the hydrocarbon that might have moved. Some of the basins of the world where a large scale migration in the tune of 100 kilometer or more that has been recorded, that is shown in the form of a table. You can see that you can have Athabasca Basin in the Canada, you have Pennsylvania, Oklahoma, that, and then the Gulf Coast. All these, they are recording some migration of hydrocarbon 100 kilometer or more, that sometimes 120 kilometer, 160 kilometer. People have traced that this hydrocarbon, they have moved so much distance because of the hydrodynamic system from its initial occurrence within the trap. So as we have discussed in our module, that the secondary migration, there are different factors which is responsible for secondary migration, and that commonly occur in the coarse grain rock. Suppose there is a sandstone where you have a interconnectedness of the pore spaces, and that gives way to the character of permeability in the system. The main force that we have seen which are operative in the secondary migration, that is the buoyancy force counteracted by capillary pressure, particularly in a hydrostatic system. And we have shown that when the buoyancy force that overcomes the capillary pressure, then there is an active movement of the hydrocarbon. We also have discussed that how a large hydrocarbon globule that pass through the narrow pore space of the sediment because of its internal pressure. In a hydrodynamic system, we have discussed that how the role of the isopotential surface of the different phases, water, gas, oil, that basically effective when you have an anticlinal reservoir, and that causes the separation of oil and gas from the one another, and there may be a downward, down dip movement of the oil which is more effective. Now, depending on that whether the dip of the structure that is less than the isopotential surface of oil, or it is more than the isopotential surface of oil, it will decide that whether there will be entrapment in the down dip portion of the structure, or there will be no entrapment in the down dip portion of the structure. We have also discussed that how we classify the basin depending on the occurrence or the exit of the hydrocarbon, that the different basins, that is juvenile basin, intermediate basin and the senile basin. People have described that the movement of the hydrocarbon for a large distance exceeding 100 of kilometers from the different basins, that also we have discussed. So, this discussion essentially I believe will give you an idea that what is the meaning of the secondary migration of a hydrocarbon, how a hydrocarbon moves to the reservoir bed or the carrier bed, because in a petroleum system, when we know that where the hydrocarbon form, we do not get hydrocarbon at that place, we get it in other place. So, there is a major role of the carrier bed, and that carrier bed, how it takes the oil from one place to other depending on hydrostatic or hydrodynamic condition, that this discussion we might have given you an idea. I believe you will get interest and go through the more books which will be referred to you in this text, and that will give you more knowledge and interest in the understanding of the secondary migration of oil. Thank you.